So, I don't know if you noticed the indoctrination going on here. We slowly moved from the normal no-code environment to the SMT solvers, and now we're getting to theorem provers, so just in case you haven't been watching. So, for the last talk, once the door settles down, we have Colin. So, please, go ahead.
All right, thank you. So I am Colin, not an imposter. This is some work I did with my student Sergey, who's back there. And I'm going to tell you about some of our thoughts on building an approach to trustworthy, formal natural language specifications. And so I should start by admitting that there's a bit of a bracketing ambiguity in that title, because we are trying to write formal specifications in a natural language, but part of our approach to making this trustworthy, we need to really understand the language we're interpreting. And so we're working in a formalized fragment, although of course, to actually make that remotely practical and useful, broadly speaking, we need to pick some foundations that we can build on and extend over time. And so a lot of this is going to address sort of what choices we've made to do that. So as Alex was alluding to, we're doing this in the context of, for us, a proof assistant, right, which are now very powerful, widely explored, big successes like, verified CompCert, SEL4, CertiCOS, and many other interesting systems. But all of these share this common serious limitation, which is, what if you formalize the wrong spec? Which we do from time to time. And there have been a number of cases, both in academia and elsewhere. And this arises from what we were calling the specification gap. This isn't a term we came up with, but it's not super common in the literature either. Which is the fact that there's a gap between what's in our heads or what's written on a piece of paper when we go to formalize these specifications and what actually we give to the proof assistant or related tools, because of course it's a human translation process and we make mistakes, right, even on easy cases. So if you want to convince a less technical user, or even a very technical user who's just not, say, a formal methods expert, you did the right thing here, how do you do that? You basically can't, unless you want to sit them down and teach them how to use a proof assistant. If you are a formal methods expert and you want to audit this, at best, in practice, there's rarely, sometimes there's careful notes about some particularly tricky corner case, but we generally don't take notes about our process. We just do it and then walk away, right? So if you want to audit this, that's hard because you basically need to sort of retranslate or reverse translate and compare one of the ends, right, which is potentially difficult. So ideally, we'd rather have a more automatically checked translation, and we'd have this in a form where we leave behind some evidence, some explanation of why, what is the reasoning behind saying this natural language is connected to this formal statement. And so our goals, broadly speaking, are we do want to write in this ambiguously parsed formal natural language. We want to make it easier to write some specifications, but our real goal is we want to extend the verification of properties we're already verifying by hand for good reasons, up through a form that we can communicate better with others. So something that we can explain more easily to non-technical users to a large degree. To make this practical, of course, we do need to make this modular, right? How many of us have made up a new word while we're writing a paper? Most of us have done it, right? So we would like to be able to say oh, I made up a new word and ship that definition in some meaningful way. And I want to emphasize that a non-goal is totally replacing the formal machinery. So especially in proof assistants, you often really need to worry about things like, oh, I need to go generalize my induction hypothesis. Oh, I need to be careful about the shape of this goal when I do induction to get a hypothesis you can use. We can't remove that level, and that's not our goal. Our goal is to be able to extend the connection from these proof assistants that we've spent a lot of time worrying about over the years. How do we trust these proof assistants? How do we trust their proofs? And extend that up into less formal specifications. So this idea of writing formal specs in natural language is certainly not a new idea, right? There's been people working on this off and on since the 70s, and it's coming back around again with auto-formalization and LLMs. There are some notable waypoints on this, right? Using the proposal to replace first-order logic with English. There was a great FSE 99 paper from the Attempto-controlled English project on that. We've had pseudo-English programming languages, COBOL, AppleScript, some of these other things. So it's reasonable to ask, like, what are we going to do differently? What's the difference? So there's a few things. One, we are doing this inside an existing proof assistant. This is not a bolt-on, this is not a preprocessor, this is not a separate tool that you then have to maintain sort of in tandem in delicate ways. So this is really part of a tool that people already use for verification. There's no, oh, you have to switch to this tool. There's no LLMs, we can talk about that later, but they're big statistical distributions and don't leave evidence. So we're supplementing, not supplanting the advanced interfaces that are already in these proof assistants. But one of the big things is we want to actively embrace the knowledge of the linguistics community, which has spent many decades carefully studying this relationship between natural language and formal language. And so we want to be able to take advantage of that. The main approach we have to taking advantage of that is by building on this thing called categorical grammars, right? So this is a large family of techniques. I have bumped into a few people who have heard this term before and they think it's just one thing, but it's actually a very large family tree of systems rooted in theoretical formal linguistics and substructural logic, which makes for a nice bridge to people working with proof assistants. So there's a long history here that I'm not going to talk about at all, going through famous linguists and logicians. They've been used to give extensive, thorough treatments of wide-ranging grammatical phenomena in English, German, Hindi, Japanese, Arabic, French, and there's more in the paper. And this is also something I have to acknowledge is not totally unknown to PL people. So there are people here, even at this conference, who have worked with categorical grammars, but mostly going in one direction, which is taking PL concepts and trying to make it easier to do linguistics better, more easily, which is very cool, and I love that work. But we are going the other direction. We are trying to raid this treasure chest of linguistic knowledge and use it to make better proof assistants, right? So the core idea here, what is a categorical grammar, what is it doing, and this is going to sound weird when I say it, we're making a type system for words, right? So bear with me. So the basic idea is we have some sophisticated way of describing the role of a word or a sentence fragment in a sentence, and the combination of those grammatical types, which we'll call categories, and certain logical rules for combining sentence fragments, get us to basically being able to parse a sentence. And one of the things that's nice about this is these categorical grammars in particular are what are called lexicalized grammars, which means not all but almost all of the knowledge for different grammatical constructs actually is localized to what's the grammatical type we give this word. Which means that if we want to support new grammatical abstractions or new grammatical constructions, new patterns of specifications, we just add new word entries. We don't have to revisit things. We don't have to go digging deep in some very funky, carefully crafted context-free grammar. We just add, here's a new way to use this word. And usually, we can read that directly out of the linguistics literature, which is what we've been doing so far. So parsing now becomes proof search, and I'll show you on the next slide in a second. It's proof search in a particular kind of substructural logic. And this extends really naturally to what's called semantic parsing, which is parsing not just the sentence structure grammatically, but parsing out what is the meaning of this by building up the meaning of the whole sentence from meanings of smaller pieces, which actually goes under this banner of the principle of compositionality in linguistics, which is kind of like their analog of what we do when we talk about denotational semantics. So here's the basics. I'll just cover a couple small rules. So the most common rule, the one people tend to start with, is this one. It's called rightwards application. And so what this rule is saying is if we have these two sentence fragments, gamma and delta, they're each some non-empty sequence of words, but we don't know how big they are. We don't care, actually. If we can give gamma, that first fragment, this grammatical type B/A, so B and A are some other grammatical categories, but the important part is that slash. This is like a directed function type. It's saying, if you give me an A to the right, that's why this is rightward application, if you give me an A to the right, you'll get a B. And so that's essentially what this rule says. If you have something on the left that would be a B, but it's looking to its right for an A, and then that delta, if we see that actually that is an A, and it's on the right, we can put them together and we have a B. And not only that, but we compose the semantics as well. So actually the fact that that first fragment has this category B/A tells us its semantics are literally a function from the representation of A's to the representation of B's. So there's a very tight correspondence here between the grammatical types we're seeing and the semantics in a type lambda calculus. So there's a leftward version of this too, because most languages have things that modify what comes after them or before them, which may be left or may be right, depending on what language you're talking about. There is this tight connection between the grammatical categories and the semantics. So the grammatical category literally says this is the type in some type lambda calculus you're using to represent meaning. And if you're worried about, can this really capture all of natural language? Is this really extensible? So these basic rules, if you kind of squint, you can see they're kind of like pieces of CYK parsing. And so these and a couple others get you context-free grammars pretty easily. Most linguists think we need a little bit more than that, and these are more than up to the task. So there are other rules that I'm not going to talk about that can get you well past context-free. So we use this by searching for these derivations, right? So if we want to try to understand the sentence 3 is even, we can do this by just breaking it down into subsequences and trying to put them back together, and we might find a derivation like this one. So if we split off 3 by itself first, we might go look at this circled bit here, where I've assumed in our database of knowledge about individual words, we have an entry that says 3 is a noun phrase and its semantics are 3, which I'm pretty sure is what 3 means. We split the other half down again, and then we have to deal with is and even. So we'll do even because that's a little simpler. So even, we assume we have an entry that says, oh, it's an adjective, and its meaning is the mathematical predicate, even. And then we get to is, and this is where we start to get a little bit of a hint of why these grammatical categories can actually cover a wide range of different uses. So this type, this category for is, this NP/S/ADJ for adjective, it says that first, is will look to its right for an adjective, and that's bound with lambda p in the semantics. Then it will look to its left for a noun phrase, which will be the subject, and that's bound with the lambda x. And then the semantics after those two things are supplied is basically the truth condition of, is this predicate we bound true of the subject we bound, right? So if we take this and we plug these in and we do the function applications that those rules tell us to, and beta reduce, we get that 3 is even is a sentence, and it means the proposition even 3, which many of you have probably noticed is not actually true, but that's okay because sometimes we try to say things that are not actually true and we want to find out that they're not true. So this is not a proof that 3 is even, this is a proof that that English is interpretable as that formal claim, right? The other thing that's useful here is this structure, right, this is a proof in a particular logic. And so our prototype actually builds this structure, right? And this is why we are calling these trustworthy, because this is something that gets persisted into, oh, you compiled the program, you used this spec in the tool. There's evidence of this remaining in the compiled output from the proof assistant that someone could go look at later as a certificate. So we took this and we crammed it into lean type classes. Somebody was talking the other day about abusing type classes in Rust. Well, we did bad. So recall that type classes are, in general, this way of getting the compiler to provide implicit arguments, to come up with certain arguments for you. It draws heavily on logic programming, right? Prolog, Datalog. It's quite popular in Haskell, Scala, although probably some Haskellers in the crowd have done worse than we did. So the core idea here is we've written something that's effectively this, and I think that might have come out smaller than anticipated, so I apologize to you in the back. I was one of the people who had to reformat their slides, and it seems to have not worked great. So the core idea is we've implemented the moral equivalent of this function spec that takes a list of strings, basically a sequence of words, and then in brackets there is this declaration that we want the compiler to provide a synth, that sequence of words, sentence instance. So come up with evidence that this sequence of words is a sentence. So when we ask, when we write code like spec 3 is even, Lean will go off and it has some algorithms to try to figure out, okay, can I find something that shows synth 3 is even s, that this parses as a sentence, where that synth sequence of words and some category corresponds to just the left half of that judgment we were seeing on the previous slide. So it's just saying this sentence fragment has this grammatical type. And then the semantics just become a member of the type class. So if you can see, or if you can't, the definition of that function, the body is just returning the semantics member, the sem member of whatever the compiler finds for us. So each rule then becomes an instance for synth, and this part is not, the fact that we're doing this in Lean and doing this with categorical grammars is the novel part, but the rest of this is sort of how type classes work. So we can write that write application rule by giving an instance that says for any gamma delta AB, if you have gamma that has category B/A, delta has an A, if they're in the right order, you get a B, and then the semantics is function application. So Lean searches through possible ways to combine this instance and all the others to find something of type synth 3 is even s. And then of course, you can imagine writing sentences as lists of Unicode strings everywhere is kind of annoying, so there's a macro so we don't have to do that all the time. So what does this look like? Basically, whoops. We'll see if that actually, there we go. Nope. All right, it has tried to disappear from the screen. All right, the one thing that I did not test on multiple monitors, of course, will fail. All right, so we'll come back to that at the end when I nix the slideshow. So what was supposed to happen was you're supposed to see that it was pretty fast. You'll see later, right? And part of making it fast is part of the work involved here, and this relies on a couple things. One is specific implementation choices that Lean made. So Lean actually went back and said, well, you know what, this is literally logic programming, these type class things. We're gonna bust out classic prolog optimizations, like we're gonna memoize everything when we search for these type class instantiations. And so then the other part of that was us rating some 1980s prolog optimizations, like difference lists and interning things as numbers, because of course, looking a number up in a memoization table is a lot faster than looking up lists of Unicode strings. But with a couple of these tricks, the thing actually ends up pretty responsive, and I will show you in a minute. So we evaluated this. We grabbed a few specifications from Verified Functional Algorithms. This is one of the Software Foundations books. Focusing on just the early chapters for now. We tried to write English as close as possible to the descriptions of basically proof exercises from the textbook, as close as we could get. And in places where we deviated, we noted why. So in a couple cases, the spec was actually ambiguous. We made it a little more explicit. In a couple cases, there are limits to our grammar coverage. We have not had time to encode all of the thousands of words in the English language yet. So I know, right? I'm being lazy. And so we ended up translating this range of specifications. So most of these are quite similar, if not exactly the same as the original. There were a couple where we had to propose some English because the book actually just said, prove this, and they didn't really say what it was. So we filled in those details. And one of the things that's interesting here is almost all of these, the translation we got out of this prototype is alpha equivalent to the exact thing the textbook hand wrote and said, prove this. So that may be less true as we go on and tackle more and more sophisticated things, but it was true for us so far, largely true. These translate in a range of times from a little over a second to a little over 7 seconds, depending on the linguistic structure of the specification, not the length of the string. And there's, if you look closely, row 8 has an asterisk, because even though I can construct the type class instance by hand, Lean does not find, hey, there's a dictionary entry for this word, is basically the step that does not resolve, but it doesn't resolve on my computer. And so this was in the submission, and this was in the camera ready. And then a few weeks after the camera ready, we have a new student, Chris, who started a few weeks ago, and he says it works on his computer. So there's a little bit of cross-platform questions happening here, so we'll have to dig into that a little bit more. Along the way, we found some interesting stuff from the linguistics side. So there's one spec we didn't translate, which if you pay attention to really what it's doing, it's not talking about the mathematical property. It's talking about the syntax of how you would write the mathematical property. So I don't know if you can read it in the back there. It says, multisets in a nested union can be swapped. So think if you know what that means, and how sure are you? So it actually means this. It means the union of A and the union of B and C is equivalent to if you swap something in the nested union and the thing in the non-nested union. So this is interesting because the whole notion of nested union, that is a very syntactic notion, right? This is talking about the syntactic structure of how you would formally express this in logic, not about the mathematical property. So we didn't translate this. We could have made something work, by hacking along, but we want to do a deeper dive into what does this look like more broadly. We expect we're probably going to see more of this as we keep going in both proof assistance and other broader mathematical literature. Also, it's slightly vague because maybe it was talking about swapping B and C on the left there. The other thing that's interesting is we ran into some type theoretic puzzles as well. So I sort of hinted earlier that there's a function from these grammatical categories to a lean type. And of course, we have implemented that function in lean. And the thing that's difficult here is that once you start dealing with talking about things in multiple universes at once, we run into problems because even though all of our machinery is universe polymorphic, so you can kind of shift it up and down in this infinite hierarchy of universes and these type theories, it doesn't really deal well right now with the fact that some things are up here and other things are down here. Like if you say every BST, that's actually 3 quantifiers, not 1, because it's actually saying for every key type and every value type and every tree of that previously quantified key value type choice. So there's a lot of interesting stuff going on there that we're going to dig into in the future. So wrapping up, we can support natural language specifications in current proof assistance with evidence because we construct it during parsing with good extensible linguistic coverage. I didn't get into like the linguistics of how do we treat certain language constructs, but everything we've done is literally read directly out of the linguistics literature. We have not had to be creative with anything yet. So this is also extensible both because of the formal foundations we picked and because we were doing type classes. So if you make up your new word in your next paper, you can just add a type class instance and ship it off, right? And that word will work. And then we found some interesting stuff for future work that I just talked about. There's more details and nuances in the paper, but now that we're done, let me actually get this on the screen. Apparently, it does not let you drag it onto the other screen if something is full screen. So this is the intended usage model. So here we have the manually proven spec, basically the one that we read out of the textbook and somebody proved. And then this is basically what we've implemented. So we have dspec, and then in these brackets, sort is a sorting permuting algorithm. And Lean has figured out, hey, that parses. That is actually a proposition. And so if we hop in here, we can see that it's asking us to prove that the original spec implies this English spec. And this is building that connection between formal and informal that we were talking about. And if we step along, we can see, oh, actually, yes, there is semantics there. So simplifying once unfolds that definition, and we get a formula. Don't worry about the details. And we can keep going, and the rest is proving a formula that, in this case, turns out to be pretty easy to prove. This is about as far away as we got from the original textbook specification. And it's mostly because that use of a in the middle of a sentence turns into an existential quantifier, because you're saying something is a, as in there exists a thing with this property. And then we just sort of rearrange some ands and ors there. And the thing that I wanted to show you, since I said, oh, you'll see that it's fast. So there's yellow stuff because it's recomputing, and this is one of our slower examples, but it's done now. So it reparsed it. And that's it. Thanks.
All right, we have questions already. Nice.
Very interesting talk, thank you. So I was wondering if you also thought about the reverse mapping of having existing specifications and generating natural language descriptions.
Yeah, so this is a really good question that we wrote quite a bit about in response to the reviewers asking about the same thing. And it turns out the reverse direction in theory works, because in theory you can just unify everything, right? But in practice it's actually extremely difficult, because without the simplification step, after I parsed that specification, you basically get a giant pile of function applications, right? But that's not how people actually write their specs. People write basically the normalized form. So going the other direction basically requires a lot of guesswork on like how, what series of reductions produce this, undo them, and then unify backwards with those rules. And that's why the people who have worked on using this technique to go the reverse direction support very restrictive fragments like and and not even quantifiers. So that reverse direction is legitimately theoretically harder.
So really interesting stuff. You mentioned ambiguity, and you said you were very careful with saying that this is a possible meaning of 3 is even.
Yes. So good question. So yeah, so we didn't run into any problems with that in this case. So the lexicon's still relatively small, so there's still plenty of room for that to happen. Our stance on that is basically, if it's ambiguous, is that really how you want to word your spec? And so the lean prototype doesn't do this. It doesn't tell you, hey, I have multiple parses for this. We had an earlier Calc prototype where this was possible. Calc type class machinery has a feature where it can warn you, hey, I found multiple derivations of this, and treat that as an error. So that's something you could, in principle, add to lean. It would base some engineering work, but it's not. It exists in Calc, so clearly it's possible.
I wanted to say this is a really interesting talk. I just had a quick question.
Sure.
Have you tried, so MathLib 4 has a bunch of formalized undergraduate theorems with formalized statements.
Yep.
Would you think, have you tried perhaps translating some of the statements you might find in an undergraduate math textbook into and comparing them with what?
So we haven't tried that, but here's the first thing I know we would run into with that, and that is the heavy use of type classes in MathLib itself. So that is actually one other thing where the use of these ideas in linguistics so far has not gone that direction, because why would you have type classes if you're just writing lambda terms on paper, right? So this is not a thing they worry about, but it is a thing we would have to adapt. And so I have some thoughts on that, but nothing is implemented.
Thanks, very interesting work. I was wondering about error messages. So what happens if you write sort is a 3, for example?
You get one of several possible outcomes. One possibility is it just says, oh, there's literally no way to do this. Sometimes it proves exhaustively this is not correct. It doesn't give you any guidance on fixing it, because it's just type class machinery. So there's room. One thing I have thought about but have not seriously investigated yet is there is a way to do plugins for lean. So maybe intercepting for this particular type class and trying to do something clever there would be useful. The other possibility is it just says, couldn't do it because we ran out of time. So something that you'll see here is I cranked the number of things it will try for the type class machinery up quite a bit. I think these are normally set to 400 or something, because it's not intended to be used for this kind of search space, really. So this is why I joke about doing terrible things with type classes, because it's not really meant for this. But I mean, the implementation's really robust, so it works pretty well, actually.
All right, thank you. I don't want to keep anyone from Portuguese tarts and tea, so we'll finish. Thank you very much, and yeah, thanks, Colin.